you. Today I'm going to introduce some optimizations based on the ZKM. So first, I will give some brief introduction about what ZKM and how it works. I think you guys have watched the last speech. Lucas has explained it's very in detail. Okay. Now, what MIPS? Yeah, basically it's another micro architecture instruction set. Okay, it's more stable, and okay, it's well established, I think. And lot of software today, I think has been implemented by the MIPS. We have a very classic use case. That's no, that's not mine, but for the blockchain, for the Web3, the optimism already use the MIPS instruction to implement a virtual machine in Solidity to do the fraud-proof verification. Yeah. Okay. So here, why we build the zkMIPS? I think we already have some very good use case. The first one is a hybrid rollup. It's help the optimistic rollup to reduce the finite time from the 7 days to 1 hour, because when we usually use the optimistic rollup, we needed to wait more, like 7 days for the withdrawal. But if we can combine the ZKP to commit the layer 2's execution, block execution to the layer 1, so we can decrease the finite time significantly. Okay. Another use case is the God network. God network is layer 2, Bitcoin layer 2. It's leverage the ZKM and the Bitcoin to implement Bitcoin level security level layer 2 that's help the developers of the Bitcoin community to build their DeFi, build their SocialFi, etc. Yeah, and we also have another big scope, another more big vision for the future. That's the integrated app. It can help us to scale any layer 1, because we are a zkVM, so basically we can run any virtual machine. Okay. So so I think we for normal virtual machine, we have an emulator and its memory space. Then we digest the inputs, programs, and outputs, and generates the outputs. Okay, but for the zkVM, okay, we have more components here. Like we need zk prover and attach with the trace from the execution in the virtual machine. Okay, and the trace here will be converted to the constraints polynomial and witness polynomial. Okay, and then we for zkVM we still digest the inputs, the programs, but we produce the final states. The states would be more like a commitment. It's not, sometimes, yeah, we got the outputs and we have the public inputs, which is the commitment of the public inputs and outputs. And for the proof, and we could also produce a proof, yeah. So, okay, so when we design a zkVM, okay, design is before the optimizations, but sometimes we need to take into everything in consideration, then we can do better optimizations in the future. Okay, so basically we are a hardware machine. We have about 70 instructions. It's be classified to type I, J, and R. Okay, and it's register based. We have 32 general purpose registers and 4 specific registers. Okay, for special registers. Okay, and it should be model design, like we have like a real CPU, we have the CPU, we have the memory, we have all kind of devices. So for all those components, we need to apply different constraints. Okay, if we use a monolith architecture, that means okay, every constraint polynomial should be combined like by the linear combination into a very large polynomial. Okay, so the degree should be very large, and it's hard to for the proving to accelerate. Okay, accelerate. So another is of course we need to support the continuation. That's the basic skills for any zkVM. And the thing is field is a hash function. Basically most I think most of the zkVM nowadays they use the stack for their virtual machine parts. Okay, so for the stack proof system, we need to consider which hash function and which field we're going to use. Okay, so of course the smaller field, the more efficient hash function we use, the less proving time we need. Okay, so so we get everything together. So the user have a program, have the inputs, private input, public inputs, and then it's being compiled to binary or MIPS binary, and then we have a proving there. The proving there will provide an executor and a bunch of a cluster of provers. So the executor will split all the execution traces in different segments, and then the prover, each prover will digest one of the segments, and then we use the stack to snag proof recursion to get the final proof. And meanwhile, we also need to generate the verifier for your program. And finally, we can deploy the verifier. Then each time you get the proof, you can verify your proof on the layer 1, like Ethereum or other layer 1s. Okay. So basically, when we execute each transaction, it's more like we transit the state from the old one to the new one. Okay, the basic register is the program counter, and another is the memory space. Okay, so also we have some other auxiliary registers. I didn't describe them here, but just for easy understanding. Okay. So each module, like I mentioned, each module will acting as a chiplet. You take a PC instruction and then run the execution, perform the execution, and get the results, and write the results into the specific register or memory cell. And that's the simple example. I think last talk. Lucas have a very detailed describe about these parts. Here, okay. So, like the left table, it's a sequence of instruction in our segment, and the right parts we have a table. Each column would be the state variable in our circuit. So each state have a trace of value, have a sequence of value, which each cell indicates that the value was used or produced in the specific row. Okay, so like the row I, we read the register 4 and the register 5, and it calculates the addition and what value back to the register 6. Okay. That's just a sample. That means that we really use the same naming in our zkV virtual machine. So when we have this big table, we need to apply the constraints on the row to make sure that each row, the values in each row meets the constraints. Okay, so basically we have different instructions, so we also have different constraints here. But when we check the constraints for each row, we need to check every constraint polynomial. So that means we need to do a linear combination of all the constraint polynomial and then apply fill the value of the columns on the right table into that polynomial to calculate the if the composite polynomial is equal to 0. Okay. Meanwhile, when all the constraint satisfaction check done, we need to commit the trace polynomial. Okay, that's why we get the 0's x, 1 the x, and n x. Usually in our zkVMs, the columns, then in the first version, the first version which means the alpha version of zkMIPS, we have about 1,700 columns. Okay, so the column, so that means we have 1,700 polynomials here. Okay, and the second one is the row size. Okay, the row size basically depends on the segment size. That means it depends how much instruction we have in one segment. Okay, and so when we want to control the memory consumption or the CPU consumption, it's the same. Okay, we need to the first skill is to adjust the row size. But if we want to really optimize the zkVM, we need to reduce the column size. Okay, reduce the column size. So here is the first optimization comes as the first is when we use a very big table. When we use one table to keep track of all the state transition, that means we have this table. We got about 1,070 columns. That means we have to commit so many columns, so many polynomials, and for all those kind of polynomials, we make out a big stack table. So and for none of the values in those cells, there may be 0 or default value, because for each instruction they actually affect very few columns in the table. So that's, I say, it's a very sparse table. Okay, so the first case we need to decompose the big table into different tables, and the different table hold different constraints polynomial. So that means the constraints polynomial would become less. Okay, for each table, for each subtable. So here we have 6 subtables, like the arithmetic table, the control table, the logic table, memory table, and hash and Poseidon table. Okay, so when we decompose the big table into smaller tables, and then we can commit each table separately, but we need to connect all those tables, make sure that the value shared between those tables are identical. Okay, that's here we go have the lookup scheme. So basically, the lookup scheme is as Lucas mentioned, we want to find a set. We want to check the two sets. We want to prove that some elements of a vector or a table can be found in another table. Okay, So basically, we can use more like the product commitment, grant product here, but it's very inefficient. Okay, so what we have here is leverage the GKR optimize lookup. Okay, you can see that the multiplication above can be reduced to the addition of the different fracture functions, and finally we can, we can apply the, we can calculate the fracture functions and apply several rows in the table. So we can use those additional table to check the lookup after we check the constraint polynomial. Okay. So so another one is we need to limit the degree when we apply the lookup. Okay. So that means if we have such a polynomial like zx equals to a the production of a, b, and c. Okay, the degree will reach up to 4 because we have a deferred degree here for each polynomial. So then we need to split the polynomial into different expressions, and we also introduce the intermediate polynomial like this z_1 1 prime polynomial. Here, so we calculate the z1x, and then we check the equivalence of the z1x and the z1x prime, and then finally we calculate the final zx. Okay, it's more like the hints in most of the ZK circuits. When we implement the ZK circuits, it's the hints skills. Most of the it's a very low skills, I think, for most ZK developers.
Looks like it's limiting the max degree to 2 instead of 3.
Basically, we have a deferred degree in the polynomial. So Okay, so basically that's all the lookup map for all ZKVM. We have the CPU, so we have the memory, we have the processor. So we apply the lookup between all those different sub-table or sub-modules. It can be checked out in our code, but it's just for the simple explanation here. We have a simple map introduced. Okay. Another very important optimization is the continuation. Okay, the continuation actually it's I think it's well known for most people right now. It's just it's help us to prove in parallel, enable the checkpoint in ZKVM. That means when we prove some chunks, it's fair. We don't need to regenerate the proof from the beginning. We can keep proving from some chunk, okay, some segments, and it also can help us limit the memory consumption when we have a lot of machine, but the machine have very low RAM or CPU, have a smaller RAM or have small number of CPUs, so we can limit the segment size and make sure that the normal or the ordinary user devices can also produce the proof for us. Okay, a segment actually is a sequence of MIPS traces with an entry program counter and an image ID. So an image ID is basically the commitment or the snapshot of a memory space. Okay, we have 4 gigabytes memory space here, and we split them into each page of the memory space is 4 kilobytes, and our image ID is calculated by the localization, and but it's not a binary modernization. It's a multi-way binary tree, a multi-way tree. So that's we actually we have three levels right now. So okay, so as we discussed before, basically here we when we run the segments, when we perform the instruction for each segment, sometimes we only change part of the address. That means we only change a small amount of the value for some address. So when we calculate a new image ID for each segment, we just need to update part of the page, and then we will calculate the new image ID for the segments. Okay, so here the hash function we are using is the Poseidon hash. It's really it's more friendly to the sockets, but basically it's not friendly to the CPU when we calculate the root page. But that's okay because we have it's the when we perform it in the out of the ZKVM, it's very quick, it's very fast actually. But when if we want to check the conflicts like the SHA-2 or SHA-3 or something other hash function in the sockets, is maybe very inefficient. So Poseidon maybe is a good options, and so okay. And then when we get the segments, we have the provers, we have the proof aggregation skills and the stack to snack skills. We can run we can generate the proof for a real Ethereum block, other virtual machines transaction like this. We split the segments, and we generate the root proof. Why we say it's root proof? Root proof basically it's the aggregation proof for all the stacks table. We have sub-body, we have the lookup table. So basically each stack table will produce a stack proof, and we need to aggregate the proof first before we really aggregate the proof for different segments. Okay, and the second part is we implement stack welfare for different for two segments, 2-to-1 aggregate, 2-to-1 stack welfare aggregation sockets. And then finally we apply the stack to snack. We use the converts the the proof from a small field to big field to make sure that it can be verified on the layer 1.
What's the relationship between root proof and the segment proof?
Segment proof. Okay. Okay. Yes. For the segment proof, basically it's consists of several stack proof, because we have different sub table, right? CPU table or memory table. Okay. The root proof is basically the aggregation of those proof. Basically it's
random linear combination
or for the stack is very simple. You just implement two stack verifier. Implement one stack verifier and then call the stack verifier 2 times, fill it with the stack proof. Okay, so it's quite different from the stack of stack aggregation proof aggregation. So we just code twice in the aggregation circuit. Call the stack verifier twice. Okay. So it's same for the aggregation proof, but it's just for the different segments. Okay, so in the following up, I will give a simple introduce about what we have the dev tools. But it's I will go this part very quickly. We have a playground, and we also have a project templates here. The templates is like the proving framework for the ZKM developers. That means we have a guest program and host program. The guest program, you implement the parts you want to generate proof, and in the host part you call the prover to prove in the guest, and you also need to fill in the inputs and get the outputs, and then when finally you use the prover, like the local prover or networking prover, to get the proof, and then you get the inputs proof, so you can then submit the proof to the layer 1. Okay, it's more like a framework. It's very easy to use. We have a lot of helper scripts that we can try some. We also have some samples there, like the SHA-2 Rust EVM and Golang EVM in the guest in the wrapper. So yeah. And okay, for the guest program, we have a very simple example here. I think Alice has some introduction about this part. Before Lucas' speech. Okay, so so that's how what we do in the host program. And then we also have a proof network. That means it's GPU enabled. Basically it's very easy for developers to use the proof network to generate the proof. Okay, if you want to run with a very big segment size, you can use the proof network. And now I want to share some of the benchmarks. We did a comparison with the RISC-V production we won when we released the beta. So basically you can see that for some simple, I need to say for some cases like the SHA-2 and SHA-3, SHA-2, SHA-3 are the simple, the run once, SHA-2 or SHA-3. But the SHA-2 chain means we run multiple times of the SHA-2 in a single guest program. So we can see that for the single proving, we are better than RISC-0 for some case, and about for the SHA-2 or SHA-3 chain, we may be slower than them. We need more time to prove it. So, but the difference is not very big. We just for that SHA-2, you can see that we are slower than them by 341%. Okay, so that means when we proving a big problem, it's we are still need more optimizations to keep up with the best to lead the performance. I think So here we still performance. I think performance is not the only one to estimate or ZKVM. I think for ZKVM first we need to take care of the dev tools, and we need to take care of the use case. Okay, that's what we are doing right now. The first one is, okay, I can give some explanation why for some big sockets we are seeing. So the first, so the best is the biggest factor is that we are using the Planck 2 with the Poseidon hash function and the God logs. Okay, so this so for the SP1 they are using for the RISC-0 they are using the like baby bear, which is a smaller field, and for the SP1 they are using the Planck 3, and the Planck 3 can offer you with different hash function and fields. Most like the Poseidon 2 or the baby bear M31. So that's the first option we want to follow up is we are going to migrate from the Planck 2 to Planck 3. And another very important feature is the upgradable pre-compares. Okay, so pre-compares is really a very hot topic recently, because it can help the ZKVM to include some stock tables, and for those stock tables, because it's already been generated outside of the prover, so you can save a lot of time when we proving those pre-compares. But here I want to mention the upgradable. That means when we add a new pre-compares, the structure of the prover may be changed. That means the word file need to be changed. If you want to, keep updating your prover and make sure that the word file on day one still still be working for your proof. Okay, you need to make sure it's upgradable. Okay, so there is a better option. The better approach here is we using the like the virtual machine in virtual machine scales. That means we have the zkVM thing. We can verify the proof of another proof, and the proof we generate is not related to the virtual machine circuit itself, but it's related to the application proof. Okay, so you get every input into public input, then you can implement some architecture like virtual machine. Okay. Another part is the BitVM2 oriented anti-verification. That means I think everybody knows BitVM2 right now. The very complex part is the middle loop calculation by the Bitcoin scripts. But basically, we have different approach to calculate the middle loop. Okay, so the BitVM officer wrappers, they are using the Artworks Group 16, and we are using the GNAC. Basically, the middle loop implementation are different, and we because thanks to the extension field we are using in the Group 16. That means the embedded degree is 12, so we can have a very significant optimization here. We don't have to calculate the vertical lines in the middle loop calculation. So here is, I think for the Gold network, they are Bitcoin network, they're using the BitVM2, they can apply these optimizations. Okay, so the next another one is the provers durability. That means when we have one prover, it can act malicious, right? So how to verify that the prover is not single points? It cannot change the sockets to produce the invalid proof. Okay, so we may introduce some technology like the trusted execution environments. Okay, so yeah, basically that's all about the optimizations today. Yeah. So any questions?
I have a question. Can you elaborate more about the lookup table? Which two tables are you comparing?
Okay. Yes, so when we decompose the big table into small tables, basically we still have a table to keep track of all the instructions we are executing, but the constraints has been moved to the small table. The constraints checking has moved to the small table. So when we commit the big table, we need we need to make sure that the value we shared to the smaller table is identical. So that means when we commit all those tables, we also need to check the equivalence of those values between the different tables.
You mean the right side table should be a subset belong to the big table on the left, right?
Yes, we use a selector to select the specific columns and then check the equivalence between the two selected table.
So the table is in the subject is the right side and the left side, right?
Yes.
Not the top versus the bottom.
Of course, we have some lookup between the sub table. Yeah, like the Poseidon, maybe it's leverage the logical calculation. So the
lookup may also
between
vertical and horizontal both.
Yes.
Okay.
Okay. Okay.
Another question.
Okay.
You in the execution trace table, you only list the values for each register.
Yeah.
But the memory is not included, right?
Basically, we have the memory. When we generate the table, actually the memory will be loaded into the register. The memory value will be loaded to the register. Yeah. So when we generate the table, actually all the columns can be considered as in the register. So that means we not only have the registers from the MIPS, we also have the auxiliary registers for the.
Should there be a column for the memory?
Of course. When we execute the addition, we may need to load the memory. It depends on what kind of instruction we have. We have tab I, tab J, and tab R. Like the tab register, we load the value from the memory into the register, and then we perform the execution.
Take the SW instruction at the SW which loads from.
Yeah, it's same words.
Oh, yeah.
Okay, same words. So like we need to save something to here.
Yeah, but it's not reflected in the column, right?
Oh yes, it's not a complete table there.
So I think the memory is the hard part to constrain because the size of the memory is much larger than the size of the 32 registers.
So basically, we just check the. First, we make sure that we can consider the memory like the access. We need to consider. Yeah, we need to handle the random access memory layout. So when we check the memory, basically we check that each address is incrementable. Yeah, so that means the address we use in the next step, the address is bigger than the previous one, and then we apply the range proof to check the address, the value on that address is in some range. So basically, for most of the memory constraints, I think
maybe not just in some range, but that you have to ensure the loaded value is the same as the last update to that address.
Yes, of course. That's correct. So when we check the constraints between the two different rules, we need to make sure that if this rule change this value, we make sure that those two values are different. But for the left of the values, left of the columns should be keep same. Yeah. So when we check the constraints between different for the memories, we need two window to check the constraints. Okay. Thank you.